All right, welcome to our session 4 for, it is not September 30th, but welcome to our session 4 for machine learning. We are officially, this marks our halfway point in the course. We have assignment 1 due at the end of this evening, and then we have assignment 2 coming up next week. And then assignment 3, I will release before the end of this week, so by Saturday evening at the latest, so you guys could start to see what assignment 3 is going to look like. And then those are all your assignments for this course. Then we'll just focus on the exam for the end of the course. So the assignments are coming to an end. Today we're going to talk about another algorithm. So we're introducing our third algorithm now. We talked about linear regression for regression problems. We talked about logistic regression for classification problems. And now we're going to talk about decision trees, which ultimately build towards random forests. And random forests can actually be applied to both regression and classification problems. However, we're probably going to talk about them primarily for classification problems because it's a really it's a really easy way to map the concept of random forest, the algorithm of it, to a problem. So we're going to start with that. Decision trees are really the foundations of random forest. So you can think of random forest as made up of a lot of decision trees, and it's sort of the wisdom of the people algorithm. You know, what do the people say? What's the majority vote is the random forest. So the way that we're going to understand random forest is by understanding the decision tree, which is the voting engine for a random forest. And we're going to talk about Gini impurity and information gain, and maybe touch on another concept called overfitting. So that is the plan for today. So we're going to start here with decision trees. Let me just, put it on the screen. Okay. So in a decision tree, a algorithm that we use for a supervised learning problem. So linear regression, logistic regression, decision trees, random forests, all supervised learning. We haven't touched unsupervised learning yet. We will, but we haven't done a topic on that yet. So this is another algorithm within our supervised learning domain. That means we have answers. We have labels mapping what the outcome was. And decision trees can actually be used, like I said, in both classification and regression tasks. And the way that it works is it splits the data into subsets based on the most important feature at each decision tree step. So it creates this tree-like structure and representation. The goal is to separate all the data so that when we get to the bottom of this tree, we have clearly separated target variables, and then we can say, based on these conditions, this is the outcome. So let's try to visualize this a little bit. I really like decision trees because I think they fit a process that we naturally go through as humans when we're trying to make decisions. So in this case, we're trying to classify maybe some animals. You see a picture of an animal, and at the first thing you think, well, is it a short animal or is it a tall animal? And if it's a short animal, we go to the left here, and then we say, well, can the animal squeak or can the animal not squeak? Well, if it can squeak, well, then we make a decision. We get to the end here and we say, well, it might be a but if it cannot squeak, then we say, well, it might be a squirrel. So this is kind of like a very natural process that we go through. The decision tree algorithm codifies this. So each of these are features. How tall is an animal? Short or tall? That's a feature. Can the animal squeak or not? Yes or no. And I should maybe have what would the data look like here? That's what I'm trying to map out. Let's see. So what would our X features look like? Maybe we would have X sub 1 would probably be height. And maybe, so x sub 1, maybe that's height, and that's, are they short or are they tall? Maybe some animals are short, some animals are tall. We have a lot of tall animals here. And maybe x sub 2 is squeak. Can they, there's not a K in squeak, but can they squeak? Let's see. Maybe they can, maybe they can't, maybe they can, maybe they can't. You get the idea. I don't know if these are real animals that I'm mapping out now at this point, but x sub 3, maybe do they, what's the length of their neck? Is it long? Is it short? You get the idea here. So there's some more things. And then there's our Y target variable, which in this case is a multi-class problem. We're saying squirrel, rat, rhino, hippo, elephant, giraffe. So squeak, yes. Short neck would probably be like, this would be like a rat, right? So this is a many class problem. We've got at least 1, 2, 3, 4, maybe 5 different classes. So maybe not the best example, but this is what our data would look like. And the question is, how do you create these nodes here? How do you determine what is the decision point at each? How do you determine what question to ask at each of these nodes? So this is what we're going to explore through decision trees. This is the algorithm that we're gonna look at. So here is a maybe a more salient example. We have data about an individual, and we're trying to understand if they are at high risk or low risk for a heart attack. So we talked about this with the diabetes problem. Here's another example. We could use a different algorithm. So instead of using a logistic regression, we could use a random forest. And perhaps we have features about a person, such as their age, their weight, whether or not they smoke. And based on this information, we can send the data through these different paths. So if they're less than 18 years old and they weigh more than 60 something, I'm not sure the units of measurement on that, they are perhaps at high risk. And if they weigh less than 60 something, they are perhaps at low risk. So at the end of the day, this is the decision that our model is outputting, high risk or low risk. So this is a 2-category problem. This is a binary classification problem, a 2-class problem. They're either high risk or they're low risk. And based on your data, based on the information about that individual, we're following these paths to predict that output. When you train your random or your decision tree, you're training it to determine which feature should it split on first. This is called a split when it sends data down these different paths. Which feature should it split on next? So so here we have trees go through this process of recursive splitting. So starting at the root node, at this decision node at the top, we hand it all of the data, all the records in our data and all the features in our data. And then based on that, runs a calculation that we'll look at to determine which feature creates the best separation in the data. When we say best separation, we mean the most separation of our target variables. So we pick a feature to separate on, and then we send features, all the data that meets criteria 1 this way, and all the data that meets criteria 2 this way. So now we've separated out our data set. So not everybody goes to this second level of node. Only the people that meet X criteria, maybe only the people that are older than 18, records go to this decision node. So it's not necessarily even separated 50-50 or separated equally, just based on the criteria for separation at the top decision node, we'll continue to separate down. So the tree starts at that root node, and it contains the entire data set. And then we split the data into 2 or more subsets. So this splitting process basically continues recursively. It's a recursive program, essentially, that continues to split the data. So at this decision node, if we don't have perfectly separated data, then we're going to continue to separate the data some more until it reaches some ending criteria. And we'll talk about what those ending criteria are. So this top node is called the root node. Just a terminology thing here for you guys. And internal nodes that represent a decision are called leaf nodes. At the end, when you get to the very bottom of this decision tree, then we output a prediction, right? We make a decision. We say, if we send some data down, different color here. If we send some data down this path and it ends up here, we're like, yep, this person is this age and they have these conditions, then at this point, we're going to output a decision. These nodes at the very end here are called leaf nodes. These leaf nodes output the decision. The way that we choose the best feature is based on metrics such as Gini impurity or information gain, which we'll look at today. Okay, I'm just supposed to whiteboard apples, bananas, and pears. I think it was what I did here made sense for you guys. We may do that or may not. Let's keep going here. I don't have a whiteboard in here. It's kind of, I'm a little slow on the clicking on the screen. Someday I'll find some digital way of doing that better.
Isn't there like an Apple Pen?
That's what I need. I need an Apple Pen, and the logistics of hooking that up with the iPad and then the StreamYard, I don't know, but someday I will figure it out.
I actually have a product that my kids use, and it was like $20-30 on Amazon, and it's its own little sketch pad, and it was just weird how easy it was for them to write on it, and it translates to the screen without getting I don't know. I find it difficult to write and watch on the screen at the same time, but it's like $20-30. You can get one on Amazon, and it just lets you scribble up on the screen.
You should send that to me.
Yeah.
Also, I was just going to suggest, do you like Miro or any sort of, so you wouldn't be able to necessarily write out, but you could type out stuff.
I'm not quite as fast or expert as Miro. I really do prefer the actual writing. Yeah.
Or get an Etch-a-Sketch, maybe.
That's what I need. Okay, let's do this. Maybe I'll pop back and forth here because I think it's a little hard to describe Gini impurity without some context here. Okay, so Gini impurity and information gain. Gini impurity, these are metrics for which we're going to use to determine which feature is the best feature to split on. So here we have apples, bananas, pears. We've got some information about this fruit, and we want to predict if it's an apple, a banana, or a pear. So I'm going to try to make a poor data frame here, and we've got our y target variable, and for y, maybe we've got an apple here, a banana here, another apple here, and perhaps we've got a pear. And we've got a couple features. Maybe we know the color. And maybe apples are red, but sometimes they're green. And bananas are yellow. And pears are also green, so that's a little confusing, right? And then maybe we've got the, I was going to say shape, but what else should we say about fruit? Can you eat the skin? Like reasonably, maybe you always can eat the skin, but do we normally eat the skin? So maybe for apples it's yes, and for bananas it's no. And for an apple again, so that's supposed to be a yes. And for this pear, it is a, oh man, I'm making all kinds of mistakes here. That was supposed to be yes. There we go. Yes, and yes. And then let me try to think of, we'll just start with that. So we've got some features, and basically you have a new fruit, and this fruit is eat skin. Such a weird feature to choose. And color, and it's green, and we can't eat the skin, and we want to predict, what is it? And maybe we don't have enough information here is what I'm going to get to, but let's look at how we can train a decision tree to make that prediction for us. The first question we have to ask is, okay, we want to make a decision tree. We've got all this data, and we're going to pass all this data to our algorithm. But once we get to this first node, I have to cough, sorry. How do we know what to split on? Should we ask the question, what color is it? And usually we try to ask yes, no questions. So how do we know, should we ask, is it red or not? Is it yellow or not? Or is it green or not? Or should we ask about the skin? How do we know which feature to ask about first so that we can get the quickest answer of what type of fruit it is? Here's how we do that. We can do that with, there are two metrics I'm going to introduce to you, which both do pretty much very similar things, but you can choose which of these things to implement in your algorithm. So sklearn is a machine learning package that has things like decision trees and random forests that you can import, and then you can change certain parameters about them. You can change the way that the model makes decisions. And one thing you can change is whether it uses Gini impurity or information gain. So let's talk about these two, Gini impurity and information gain. So Gini impurity measures how often a randomly chosen element would be incorrectly classified. So we want to reduce the impurity after each split. So in this case, we have all of this data, and we might say, oh, this is really impure because we have a mix of apples and bananas and pears. But if we split on eat the skin, yes or no, and so let me just do that. Eat skin. If we say, let's make this one the no, and we make this one the yes, well, we only have one record that is no, and it's just bananas. So this is one record, and it's bananas. And for the other one, we have two records that are apples, and one record that is a pear. And this is a bad example because it's a really little data set, but it's a good place for us to get started. Here, there is no impurity. So this is something called a pure node because it's all of one class. So we would say, yep, we're done. We don't need to split anymore. There's no data to split anyways because it's just one record. But even if there were 2 bananas or 3 bananas in here, it would be a pure node. And this feature would perfectly separate out bananas. If we ask if we can eat the skin or not, and all we have are apples, bananas, pears, that feature, eat skin, perfectly separates out bananas. So when we say it's pure, we mean that there is no mixture of outcome labels in the data set that we pass to each of these nodes. So the point I'm trying to emphasize here is that not all of the data gets passed to every node. That's kind of the magic sauce of decision trees. We're breaking down this data into subsets in order to make decision, in order to get to an outcome here. So if you pass me a new feature, like we look at this one and we say eat skin, yes, it does not go down this no path. It instead goes down this path, for which we have some mixed labels here. Okay, so that's Gini impurity. Gini impurity, we'll look at that a little more. I just wanted to explain what impurity means. Impurity means there's a mixture of labels. The goal is to reduce the impurity as you progress down the tree. So maybe you'll have a lot of impurity initially, and as you go through more splits and get closer to the leaf nodes, we're reducing the impurity. The second thing we're going to talk about is information gain, which is based on entropy, which is a physics concept, a physics term here. And entropy measures the reduction in uncertainty after splitting. So we're going to measure the entropy before, the entropy after, and then we use that to calculate information gain. So the higher the information gain, the better the split. The more reduction in entropy. Entropy is a system. It's like disorder of a system. The more reduction in the disorder of the system, the higher the information gain, the better the split. Okay, let's look at an example for Gini impurity. Let's be a little more tangible here. Suppose we have a data set where we want to classify whether students pass or fail an exam. It's our pass-fail exam. And here is the data for a node. We have 4 students in class 1, which is of the label passed. So we have 4 students in class 1, and we have 6 students in class 0. I would like you guys to try to calculate the Gini impurity. The way that you calculate the Gini impurity is we're going to calculate the proportion for each class. So 4 plus 6 means our total is 10. Okay, that's our total records. So proportion for each class. Proportion for class 1 would be 4 out of 10. Proportion for class 2 would be 4 out of 6. Or 6 out of 10, sorry. And then square those proportions. So we're going to use this formula. The Gini is 1 minus the sum over every class for the probability squared. And in place of probability here, we're going to represent probability as the proportion of each class. So calculate the proportion of each class, square the proportions, sum the squared proportions, and take 1 minus that value to calculate the Gini impurity. Spend maybe like 2 or 3 minutes here thinking about that and trying to calculate that, and then I'll move to the next slide, which has the answer. Oh, to your question, Luke, maybe I answered this earlier. If I like Miro, I was impressed with the way you used Miro when we talked about that in office hours. And now I'm committed to trying to get more expert at it because I thought that was a really useful way of applying that tool.
It's good for some stuff. It's not. I don't think it'll probably be very much better than this for writing, but you can write in it too. I think it's just nice to have an infinite board, where you zoom in and zoom out.
Yes. I'm kind of a Draw.io fan. You guys have ever used that? It's really, really simple, really rudimentary, but it just gets the job done. Okay, what do we think here? What's the proportion for each class?
The proportion for each class, I got 0.4 and 0.6 respectively.
Perfect. So we have, I'm going to call this 1 and 0 because that's what, so 1 is 0.4 and 0 is 0.6. What did we get when we squared them?
When I squared them, I got 0.16 and 0.36.
Perfect. And what did we get when we added them together?
0.52.
Got it. And what did we get for the end Gini impurity?
It would be 0.48, not negative 0.48, right?
Perfect. Correct, 0.48. So here we are. You guys calculated the Gini impurity. And this is exactly the way this algorithm works. So we calculated the Gini impurity for passed and failed if we sent this to, if we had a feature about these students and we sent this data to the node, the Gini impurity would be 0.48. Basically what we do is we look at each feature in our data set and we calculate if we split on this feature, what would this Gini impurity be? What would the separation of these classes be? Would we then have 3 and 7 students? So maybe we split on a different feature. This was like feature 1. And maybe we split on a different feature and it was feature 2. And when we split on feature 2, we had a different separation. We had 3 and 7. And I think what you guys will see if you run this calculation is that gives you a different Gini impurity. And it's actually going to give you a slightly better Gini impurity because you're getting more separation. You're getting the goal, a perfect score would be 0 and 10 or 10 and 0. That's perfect separation. That's the ultimate goal. But this is how we can actually mathematically quantify the quality of a feature to separate on in a decision tree. So, yep, you got this. I have this here. Those are just the steps that we went through. So, passed, failed, and we calculated those and had that 0.48. Okay, let's look at let's build on this and look at a slightly more complicated example. Suppose we have a data set that classifies animals into 3 categories. We have dogs, cats, and rabbits. And here's the data for a given node. We have 5 animals, 3 animals, and 2 animals in each of these class 1, 2, and 3. Can you guys calculate the Gini impurity for this? So we're extending beyond 2 classes to 3 classes. Just spend just a minute on this. Let's see, 7:12. So maybe I'll check in at 7:13, 7:14. All right. What did you guys have for Gini?
So for the, you want the final answer? I got 0.62.
Awesome. 0.62 here. So we have our proportion of our classes. We have 5, 3, and 2, which means we have a total of 10. Again, I tried to make it easy on you guys. 10, gets easy probabilities here. So we have 0.5, 0.3, and 0.2 for probability of dogs, cats, and rabbits. Then we're going to square those numbers. Then we're going to add them all together. Then we're going to take 1 minus that number to get us to a Gini impurity of 0.62. So even when we don't have just 2 classes, even when we have 3 classes, 4 classes, 5 classes, we can measure the impurity of those labels. And it's kind of fun to know how this works, because then you guys can start playing around with this, and you can ask yourself, well, if I had 1 animal here, 2 animals here, and the rest were in this class here, so we had 7, 8, 9, 10, so 10 still as a total, how does that change the Gini impurity? So you can kind of run that calculation, and you'll see that Gini impurity go up. Or maybe we do 3, 6, and 4, so 3, 3, and 4, and you guys can see our Gini impurity. So Gini impurity will go up here. Gini impurity will go down here. So I would encourage you to kind of like play around with that, see how that number changes and shifts. And that gives us a really, really good foundation for understanding how this works. So we've been looking at Gini impurity, though, as a one measurement applied to the grouping of classes. However, I just want to highlight that in our data set, we probably have a lot of features. So if we are, so in this case, if we're trying to predict some outcome here, we have several features. In this case, we have age, and we have an age feature, an age column, and the age column has different values. It has youth, it has middle age, it has senior. So there are 3 different types of values within this column. We also have an income column, and their income can be high or medium or low. We also have a student column, and the student can be yes or no. And we have a credit rating column, and the credit rating can be fair or excellent. Maybe we're making a model, or we're trying to decide like whether or not to approve somebody or something, whether or not we should approve them. But my point here is that we calculate the Gini impurity for every single split. So we could split on, are they, for the age column, are they youth or not? These are yes, no questions. Youth, yes or no. Middle age, yes or no. Senior, yes or no. So we end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 split possibilities. So there's 10 possible splits. When I say a split, I mean that first, whatever node we're looking at, and maybe the first node for this case in a tree. We're trying to ask, what should we split on? And we're looking for a yes, no answer in this case. And so when we're looking for a yes, no, we're asking a question not just to each column, even though we only have 4 columns here. Each column has multiple values in it, so we could split on any of these values. So here we calculated the Gini impurity for this, the Gini impurity for this, Gini impurity for this. So we can see, and if we average these Gini impurity for this column, this is actually the best column to split on the age column, because it has a lower Gini impurity compared to these other columns. Okay, so this is how you calculate it, but in reality, the algorithm's applying this, it's doing the math a lot. So there's a lot more math going on. So that's one example of calculating it. And then we use these computer programs because they can do much faster and larger sets of math equations than we can. Okay, the next piece we're going to look at, just touch on here, is entropy. This is a different way of thinking of how to determine the splits in the algorithm. And this one measures the uncertainty or disorder in the data set. So we're going to use the same probabilities here, but instead of squaring them and summing them together, we're going to negate the negative here, because remember, log's going to give us, it's log base 2, and remember that's going to give us a negative sign. We learned that last time. But we're going to take the log base 2 of the probability times the probability over all of those classes, sum that together, and then negate the negative. So here, let's work through this example. Let's suppose we have our same data set here. We have 4 students and 6 students. Apply this entropy formula. So log base 2 of those proportions times the proportion, sum those together, negate the negative, and tell me your final result here for entropy. 2 minutes, 7:22. And actually, I am going to combine this with our break because we're almost halfway through. Let's come back. Let's come back at 7:37. How does that sound? All right. What do you guys have here?
I got. Hang on, let me. My chicken scratch. I got 0.97.
There we are. Perfect. So we're going to calculate the probability of each of our classes, like we did before, 4 out of 10, 6 out of 10, 0.6. And then we're going to take the probability times the log base 2 of the probability, and then we're going to negate that negative. You can do it now or you do it at the end. It shouldn't matter. And then we're going to add those two things together, here and here. This is just the working out of those logs. We're going to add the end results of that together, and that gives us 0.97. All right. Here's a walkthrough for you guys, another resource. I think that is good. I try to link these in the presentations. Another resource for you guys to check out here. Actually, I know I have a notebook too. So hold on. Keep this. Okay, if we wanted to code this into a program, we can look at how to code the Gini impurity. So we could take in our passed and failed student example. We could make a function called Gini impurity. We could take in passed and failed. So in this case, we said 1 and 1,000, and we could make the total passed plus failed. Then the probability of pass is the passed over the total, and the probability of failed is the failed over the total. And then we could, this only works for 2 classes, of course. We could raise that to the power of 2, return the Gini, and then calculate this. So let's play around with this. Let's say one student passed, and we separate this. If we separate on this feature, one student, it ends up that it gets separated into 1 student passed and 10,000 failed. We can calculate our Gini impurity, and that looks pretty low. What if we swapped these? So this was 10,000 and this was 1. It's actually the same. So the order of the classes does not matter. But what if we had this? We get a Gini impurity of 0.5. So this is actually the highest Gini impurity that you can get. So Gini impurity ranges from as close to 0 as possible. What's a perfect split? A perfect split would be 0, 50. So Gini impurity ranges from 0 to 0.5. So a Gini, as you guys are looking at Gini impurity and trying to interpret it, this is a bad separation, 50-50. That doesn't help our model. We're not getting any more information. That's like a coin toss. So that Gini impurity is 0.5. So Gini impurity ranges between that and 0.5. If we had like 25 here, we can see we get a slightly different Gini impurity. You can see Gini impurity goes down, essentially, as we get to better and better separation. Okay, so you guys can play with this. One exercise I sometimes have students do, but I think I just have the code here for you guys, is to, one second, let me update my document here. Is to imagine how we might do this in a more generalized fashion. So in this case, the problem with this is it's constrained to 2 classes. I'm particularly asking for passed and failed, and saying probability of passed to the power of 2, probability of failed to the power of 2. Remember, we looked at 2 class or a 3 class problem. What if we had a 3 or a 4 or 5 class problem? and we could generalize this formula. So let's rewrite this Gini impurity to handle multiple classes. We can use this fancy little thing called the star operator, the asterisk, to have it take in class counts, which enables us to pass a series of parameters to this and then for it to perform dynamically with those. So we're going to take the sum of these things and put that into total. And then we're going to take 1 minus the sum of count over total to the power of 2 for count in class count. So this is something called it's kind of operating like a lambda function. We could do a for loop. Essentially, this is a for loop, but this is a maybe slightly simplified way of writing a for loop. So we're getting the p here, and we're taking that p to the power of 2 for each of the counts, for each item inside of class counts. And then we're returning Gini. So in that problem where we had 532, we said that the Gini impurity was 0.62, and maybe we wanted to play around with that. And we wanted to see, one question we had is what happens when we change it to 821? Oh, wow, Gini impurity changes to 0.42. What if we change this to 1000? Gini impurity changes to 0. Okay, what if we make this 555, because I want to see what the worst Gini impurity we can get is. 0.666 is what we get here. Oops. So the worst we got out of that was 0.666. Let me change this to 10. Same thing here. Because we have 3 different classes, but if we add 10 and 10, that would be 0.5, 10, 10, 10. We can see that gets to 0.75, 79. So basically what I'm trying to emphasize here is Gini impurity ranges from 0 to 1. So these have different values. Gini impurity ranges from 0 to 1. Oh, that's slightly different from what I was saying above. Never mind. I was trying to think of entropy here. So this ranges from 0 to 5. If we get into a multi-class problem, we saw that we can kind of force it to have some different results here. This is how some code that you guys can use if you want to play around with entropy as opposed to Gini impurity. So these first 2 are Gini impurity. This last one is entropy. So we can calculate entropy. We can take in pass-fail just like we did before. And then entropy is that negative of the probability of pass times math.log base 2 of probability of pass. And then that same thing for the other class, probability of failed. This line here is just making sure that we're not getting a 0 error here. So this is handling the log of 0. We can't take the log of 0. So this is handling that case. Outside of that, this runs for entropy. This is what I was trying to say. I apologize.
When do we use entropy and when do we use Gini?
So this is up to you. We have sklearn decision tree. sklearn has this decision tree classifier package, and you can either pass to the criterion to use Gini, entropy, or log loss, and the default is Gini. So when you call the decision tree classifier in sklearn, here, by default, it's going to use Gini to split. If you want to switch it to impurity, you could. I'm just trying to show you guys that there are different parameters that you can change in these models, and that you can change the algorithm, basically the way that the algorithm makes a decision. So we can do that. I think we do that down here in a little bit. So I won't Maybe I will. Let's just do this. Let me make a new. All right. Let's random forest classify. No, actually, let's do decision tree. Let's just start with the decision tree. It's not ensemble. It is a scalar.tree. Okay. So you can either Gini-based tree or an entropy-based tree. And I'll put these on different lines here. So by default tree equals decision tree classifier. So when you call the decision tree classifier, we're instantiating a default version of this decision tree. And this is just the base way to do that. When you do that by default under the hood, it's defaulting to criterion equals Gini. So we can be explicit with this if we want to, and particularly say this. We're just saying this for other humans because it's actually the default, but we're telling, we're hard coding this value that we want the decision criteria for feature splits to be of Gini. You could change that though. If you wanted it to be an entropy-based tree instead of splitting on Gini, apologize there, we could pass a different parameter. I don't need to keep doing that. Pass a different parameter here of entropy to change it to an entropy-based tree. Okay, did that answer your question? Okay, perfect. Excellent. Great, so that's in there. We're gonna keep going here because I wanna get to random forests. Let me see if now is the right time for, okay, this is a fine concept to introduce because I think we're talking about this for all of, yeah, we are gonna. I always get lost on, it's under slideshow there, presenter view. Okay. So one concept I want to introduce to you guys here is something called overfitting. Overfitting is when our model performs really well on the training data set. We give it a training data set and its performance is very high. And but it's too good. It's almost too good. What happens is it's not actually learning patterns from the data. It's actually straight memorizing your training data set. And it's remembering every example and kind of overmapping patterns that don't generalize to new data that it hasn't seen. It doesn't generalize to other cases outside of that. So the model performs very well on your training data, but very poorly on unseen data. And this is why we don't use, or it's not very common, I suppose, to use decision trees. They're not very, you don't see a lot of decision trees put into production and actually used as performant machine learning models because they have a high likelihood to overfit to your data. They're too simple. But what we're going to learn about are random forests, which are extensions on this decision tree algorithm that perform much better. Remember the wisdom of the crowd thing. What if we trained a bunch of different decision trees? And just like we as humans are different, we're going to make these decision trees slightly different. We're going to enforce some differentiation in these decision trees. And then we're going to ask them all to make a prediction. And then we're going to aggregate the outcome of that. So we're going to see what the majority vote is from the tree. So overfitting, I have a particular example of overfitting. When at one of my jobs in the past, we worked with these outreach programs. We worked with students, and they did these job fair career day things. And we're trying to think of how do we like teach people what it's like to be a data scientist, to work in data science. And so we came up with this idea of, it turned out these students really liked music. And so we found a data set online that was created by high school students in Switzerland. And they made this data set of data that they liked. And we trained a decision tree over that data. If you told me some information about yourself, if these students submitted some information to us, we could predict what types of music they liked. So we trained this on a decision tree, knowing that it would do something called overfit. And so the students came in and they told us what information they liked. And they found it quite hilarious to see what the recommendations were from this model that we had trained. And we asked the students, why do you think that this model did so poorly? And they came to the conclusion that that data set wasn't, once they opened up the data set and looked at it, they found that it wasn't relevant for them. So this was a data set of students in Switzerland, and it probably worked well for people who were in Switzerland, but these students were not in Switzerland. So the model became really, but it was a performant model, but it was really good at memorizing that data and that pattern, but it didn't generalize to the overall data set. So there's a couple problems in that, in there beyond just overfitting of a decision tree. But I think it gets the point across that some of these algorithms can be very good in one area, and we want it to broaden and to be able to apply to other concepts, not just that one area. So there are a couple of things that you can do to decision trees to make them perform better. You can do some pre-pruning. So if your decision tree is getting very deep, you're having a lot of splits, and it's getting really nuanced and edge casey, and you find that your leafs, you're having one or two records that are being used to draw a conclusion, maybe you could do some pruning, some early stopping. I'm not going to focus too much on this because ultimately we're just trying to understand decision trees so that we can understand random forests. The advantage of decision trees is that they're very easy to visualize, and they're really easy to interpret and understand. They can handle both categorical and numerical data, and more importantly, there's no assumption of linear relationships. So they don't assume linear relationships between those feature and target variables, so they can handle these more complex situations. Let me do this first. The disadvantage of decision trees is that they are going to overfit to your data. They're really prone to overfitting, especially when trees grow too large and they're too deep. They're fairly unstable, so small changes in the data set can result in large changes in the tree structure, and they have bias towards features with more levels. So decision trees are very biased. Here's a maybe more particular example of overfitting. This is, we have this best fit line. Well, if we went through every single example here, this is an overfit model, and it's really great on this training set on this right side of this picture. However, if we introduce a new point here or a new point here, it's always going to have some significant error on our new points because it's overfit to the training set. It's not generalizing to the data. Whereas if we introduce those same new points here and try to introduce them, maybe it's approximately here, and maybe this one's approximately here, this is going to have a much smaller error on unseen data, on new data that this model has never seen before. One thing, so we can do regularization with trees to reduce overfitting. So there's a couple techniques you can apply that I'll leave in these slides for you guys. But again, we'll focus mostly on random forests. On decision trees, I will say there's one more piece of utility in which I found decision trees very useful. There's something called proxy modeling. So if we have a very, very complicated model, a really complicated random forest or a really complicated decision tree, or I'm sorry, really complicated neural network, and the business wants to know how is your model making the decision or what's influencing that model's decision. At times, I have taken the model outputs of my complex model and then trained a decision tree on that in order to visualize in really one simple tree the way features that could be influencing or most important to that model. It's called a proxy model, so it's not actually modeling the way that the data is being fed or interpreted by the model, but it's a proxy representation of that. So we're oversimplifying it into a few categories, oversimplifying the data into some categories that are maybe easier to understand. Okay, let's talk about random forest. So we have a decision tree. We know there's some problems with it, some overfitting, but we like it. It's simple. It doesn't have assumptions of linearity. So how can we leverage this? We can basically, what if we had not just one decision tree, but a bunch of decision trees? Just like we have a bunch of people, and these people have different perspectives and different experiences, and they come to different decisions and different outcomes. But generally, there's this kind of fairly proven rule that if you ask a lot of people, you're going to get closer to the right answer. Okay. So wisdom of the crowd, wisdom of the people. That is the concept behind random forest. So random forest is something called an ensemble algorithm. I'm a big fan of ensembles, by the way. It's another key term for you to be familiar with. An ensemble algorithm just means we're using more than one model to make a decision. And in this case, we're using a whole bunch of decision trees. So trees make up a forest. That's why it's called a random forest. We're going to dive into the random part of it in a little bit. The random part of it is how we make the trees different. It's not useful if they all make the same decision. We want them to sometimes make different decisions, make them a little different, just like we make people, people are a little different. So random forest is an ensemble learning algorithm. We can use it for classification or regression, and it builds multiple decision trees during training, and it trains those trees to generate output. And we take typically the majority vote across these trees. So here in this random forest, we have an instance of a random forest, and this random forest, in this case, is made up of n trees, but let's imagine it's 3. We have 3 trees in our random forest. And we've already trained this random forest to make its outcome, so it already knows what features it splits on where. We pass it a new piece of information, and you can see this random forest, the information goes down this path. In this random forest, it's split differently than that one, so the information goes down this path. And in this random forest, the information goes down this path. So at the end of the day, they cast their votes, and this says Class B, and this one says Class B, and this one says Class A, this one says Class B, and this one says Class B. So the final output recommendation from our random forest is Class B, because it's taking a majority vote. 2 out of 3 people said Class B. Random forest is a great algorithm because now we're reducing our likelihood of overfitting because we're combining the decision from multiple decision trees. So it's fairly robust. It can handle large data sets with high dimensionality. We're going to get better performance because of that reduction in overfitting. We're going to generalize more to our unseen data. And it's a lot more robust to noise, to noisy data, to data that doesn't perfectly look, it generalizes more, essentially. Okay. Let's talk about how this works. There's a random element to random decision trees, and it's random across 2 dimensions. We have a data set here, and this data set has features, right? X sub 1, X sub 2, X sub 3, all the way up to X sub n. And then we have our target variable, y, what we're trying to predict. And then we have records too. So we have row 0, we have row 1, we have row 2, all the way up to row n. Okay? Dot, dot, dot. In random forests, when we are looking to pass this, I don't have a picture until later, I think, so this is good. When we're looking to send this information for training, before we have all these untrained trees. So we said, hey, we're going to create a random forest, and there's going to be 5 trees. 1, 2, 3, 4, 5. But at first, those trees don't know what node to split on. Remember, we have to go through a quantitative exercise to determine which node to split on, which feature to split on at this first node. So they're not created yet. So when we go through a training exercise and we pass this training data to our decision tree, we're not passing all of the information. We're going to pass a subset of features. So a subset of these. Let's say this one gets x sub 1, x sub 3, and x sub 4. Let's say this one gets x sub 3, x sub 4, and x sub 5. Let's say this one gets x sub 1, x sub 5, and x sub 3. Let's say this one gets x sub 2, x sub 3, and x sub 4. Let's say this one gets x sub 1, x sub 2, and x sub 5. So they are not all given the same features. Now we have this data set here, which I guess it goes from 1 to 5. We have 5 features. Each tree is only getting 3. And they're getting different features. And they all get Y because we're training. They don't get Y when we make a prediction, but they get Y during training. And then they also get a subset of records. So random in 2 aspects. We're sending random features and random records. So we're also going to send a subset of features or records. So maybe there's 100 records in our data set. This tree gets 33 records. Oops. This tree gets 33 records, and they're not the same. Maybe this one gets 35, and just because 33, 100 doesn't divide exactly evenly, but I should have done 34, but that's fine. So they get a subset of the data and a subset of the features. So they don't get all the columns, and they don't get all of the people. So that makes these trees different. The end result is, because this tree was trained on features 1, 3, and 4, maybe it says, oh, I'm going to split on x sub 1, and then I'm going to split on x sub 3, and that's how I'm going to use it to make my decision. Then I'm going to split on x sub 4 over here, and that's how I make my decision. This one doesn't have x sub 1, so it can't split on x sub 1. But maybe it splits on x sub 3, and for some reason that's perfect information for it to make its decision. So these trees are different, and it's random. They're going to look different. They're going to make different decisions because they're given different information during the training process on purpose. Okay. So let's talk about these 4 bullet points now here. Step-by-step process. The first is bootstrap sampling. Sometimes you'll hear it referred to as bootstrap sampling, but that's randomly selecting samples from the training set with replacement to create multiple subsets. So we have multiple subsets. That's this piece here, this subset piece. That's at the sample level. If we say sample, we're talking about rows here. We're talking about people. So bootstrap sampling, note that it is with replacement. So if you have one person, they can be in multiple trees. So we're going to sample 33 people, put those people back into the sampling pool, resample. So sampling with replacement. The next piece is we're going to build multiple decision trees for each subset. We're going to build a decision tree, and we're going to do random feature selection. So at each node, only a subset of the random features are considered for splitting. And then we're going to aggregate those predictions. So whatever these trees say, we're going to somehow either do majority voting if it's a classification problem, or if it's regression. Remember, regression is numerical. If we're trying to predict the price of a house, we'll just average across all of these trees. So if one tree says 100, the other says 50, we'll just average. So bootstrapping, I think I kind of described some of this on the other slide. I jumped ahead of myself here, but this is fine. Bootstrapping is a resampling technique used to create multiple subsets of data. So multiple subsets of data from our single data set. Each data set that we're passing to each tree is known as a bootstrap sample. It's generated with replacement, meaning the same data set can be selected multiple times. So that data set can be used to train multiple trees, but it won't be used to train all the trees. In the context of random forest, the bootstrapping is used to train each decision tree on a different subset of the data. And this promotes diversity among the trees. So that's why this algorithm is less prone to overfitting, because it's seeing a varying representations of what the data could look like, which is more common or more relatable to the real world. So in bootstrapping, sorry, I feel like I whiteboarded this on the other slide. On bootstrapping, we have our original data set with 100 samples. We create subsets by randomly sampling with replacement. And then for each of those samples, a new bootstrap sample is created. Each tree gets a bootstrap sample for training. So for example here, if our data set is A, B, C, D, E, a bootstrap sample 1 could be A, B, C, C, E. So this point, I do want to emphasize the same person can be in there more than once. Look, we got C in here twice. Here's our data set, A, B, C, D, E. It's sampling with replacement, which means every time we sample, we could pull that same record back. Here, in this case, we have A, B, D, E is bootstrap sample. And this would go to tree 1, and this would go to tree 2. Okay, each tree is then trained on that, which builds some variation in our trees. So the next part of the process, we said, hey, we're going to bootstrap sample on that first slide about the process for building a decision tree. The next step was build multiple trees. So I think this part is fairly self-explanatory, but we have this subsample of this bootstrap data here, and we're going to pass that to different trees. And those are going to, because there's different data, and now you guys know how Gini impurity works and how entropy works, and you know that if we have different representations of data, that's going to create different probabilities for the classes that we're trying to split based on feature determination. And so because of that, we end up getting different trees. So this is repeated for however many trees that you want to create. In sklearn, there is a parameter. We're learning about parameters and how to adjust parameters in sklearn models. In sklearn, there's a parameter called n_estimators. That n estimators, that's number of trees. So if it's equal to 50, you're going to get 50 trees. If it's equal to 100, you're going to get 100 trees. A reasonable question might be, well, how many trees should I put into my random forest? I think it depends on a lot of factors, on your compute power, on the size of your data set, the number of features that you have. But if you're working with like a reasonably contained data set, you can do like 100, 150, 200 trees, no problem. If you're working on, it just depends. If you're working on a very expansive data set, you have a lot of features, a lot of splits to do. I would play with that parameter and test it out. I want to say the default is 50. Let's look. Great. 100. Sorry, the default is 100. So N estimator's default is 100. We're going to look at an example in the code here in just a little bit. Okay, so we took a subset of the records. We also take a subset of the features. In a decision tree, the difference between a decision tree and a random forest, even though a random forest is made up of decision trees, the decision tree algorithm by itself, if we just implemented that not as a component of the random forest, but just by itself, it takes all the features into account and then trains a tree. The random forest only passes a subset of features to each tree. So this tree got feature 2 and 3. This tree got feature 1 and 3, and use that to train its decision tree. So each tree grows independently. They don't interact with each other. They don't depend upon each other for creation. And it continues to, each tree continues to split recursively to create those splits until some stopping criteria is met. This stopping criteria can be, yep, I have perfect, Gini impurity or perfect, I have perfect impurity in my nodes, or perfectly pure. There's no impurity in my nodes. Or if that's taking too long and you want to introduce other stopping criteria, we can use these parameters in sklearn. We can set a max depth parameter that says the tree can only reach a max depth of 7. You can only split 7 times and then you're done. Or you can only split 10 times or 25 times. So we can determine max depth for our tree, for all of our trees in our random forest. If we want, we can enforce how the minimum number of samples needed in a node in order to split. We can say you must have 3 samples in order to split. This will help our decision trees from making very nuanced edge case decisions based on small pieces of data. And this will enforce the tree to only make decisions if there's enough evidence, essentially. And then the obvious stopping criteria is if the node is pure, which means purity means it contains data points only of one class. That's what we mean when it's pure. And you guys saw that from the calculations we ran. Okay, so in random forest, there's no pruning. They're typically grown to the full depth. You can implement stopping criteria, though, to help adjust for that. And then at the end, we finally aggregate the prediction. So after all the decisions have been built, in random forest, for classification, we'll use majority voting. And for regression, we'll typically just average. So it's typically an average here. All right, key concepts from random forest to keep in mind that this is an ensemble method. This is the first ensemble method that you guys have been introduced to. I think this is the only ensemble method that we'll talk about in this class. And this means that it combines the predictions from multiple models. That's what an ensemble is. The random forest is performant because it introduces a lot of diversity among the trees, so they make decisions in different ways. And this random forest actually outputs a pretty good accuracy. So when you guys are building your first model, before jumping straight to neural networks or really complicated and sophisticated algorithms that maybe take a lot of work or a lot of care and feeding for implementation, I would recommend just trying a random forest. Random forest is my go-to for a baseline model. When I just need to create a baseline model and just see how performance measures beyond randomly guessing, I implement the random forest. So I try to build models in this 3-step phase. 1, let's see what random is. If I just guessed at random, what what would the outcome be? And it's not always 50-50. So it's important to think about that for your problem. For example, if we're guessing one of three classes, 1, 2, 3, that's not 50-50 anymore. If I create a random guessing machine to predict one of three classes, we can even do this in our code. We can create a random thing. So determine what random means for your problem, create a baseline. You want a model that performs better than random. And then on top of that, the next thing I do is implement a very simple, very fast, very easy to do model, a baseline model. So random forest is usually my go-to for that. It's a very good algorithm, doesn't need to be linear. It's fairly dynamic and it performs pretty decently. And then any algorithm I can have beat random forest, then you can start to introduce that complexity, introduce more complicated algorithms and approaches to increase that performance. Just implemented a random forest for one of our things last week. It's a really good place to start. So random forest can ranks the importance of features by measuring feature importance. I think is something that we should talk about, and I think it is in the slides here. Yep, in 3 slides. One really important thing with random forest that's particularly useful is it can output a metric called feature importance, which tells us how often that feature is used across all these trees. So if you have 50 trees, how often is X1 used as an important feature? Important mean used at the beginning of the tree for splitting. So we can measure which features are the most important, which features are influencing the outcome of the decision of all these trees the most. And that feature importance we can use to inform why is the model making this prediction. So a lot of times, whoever you're serving the model to, your business or your stakeholders, yes, it's great you're making a prediction, but in order to build trust, you need to answer why. Why is it making that prediction? Feature importance can help us tell that story. And it's non-parametric. Okay. There are a lot of parameters you can change in the sklearn model. Wow, we can change n estimators, which is the number of trees. We can change the criterion, which we talked about as the way that splits are made. You can make it Gini or entropy. We can change the max depth. We can change the min sample split, the min samples leaf, the min weight fraction leaf, the max features, max leaf nodes, Gini impurity. Wow, this is getting to be a lot. Oh, wow. There's quite a bit of things that we can change here. We're given a lot of control over this. Where do we even start? Here's my recommendation. I would start with these 4 things. I don't think you need to get too nuanced about things outside of these 4 things. I think if you're going with that process that I recommended, do random, then a quick and dirty baseline model, you can get a fairly performant thing with these 4 things. These are going to have some of the biggest influences over your model's performance. Of course, there's always edge cases, and it's particular to your use case. But I think generally speaking, most of the time, these are going to have the highest influence. And maybe it's 5 things, because actually the last one is 2 parameters. And estimators. This is the first one I would focus on. How many trees are in your forest? So a couple of reasonable things to try here. 50, 100, 150, depending on your data set, 250. Those are a couple of reasonable parameters to try. 50 trees, 50 decision trees, 100 decision trees in your random forest, 150 decision trees in your random forest, 250. Max depth. This depends on your problem and how many features you have. But you could try something like 7, 15, 25, 30. Maybe I put 25 and 30 too close together, but we'll make this 20. Oh, not 250 though. Max features. So the number of features to consider splitting at each node. I think the way that they have this set up is actually default is square root. So we can look at this. The default is the square root of the number of features. So whatever the length of your features is, however many features, we take the square root of that. So if you have 16 features, the square root of 16 is 4. So 4 features would be passed to each tree. If you don't think that's enough, you can change that. You can change it to one of these other attributes, or you can pass exactly the exact number that you want it to have. Even more, I think this one's useful to know how it works. Potentially you can change that, but even more impactful is min samples at split and min samples at leaf. This is going to reduce the overfitting of your tree. If you find that your decision trees are making really nuanced decisions, you can change the minimum number of samples required to split a node and form a leaf node respectively. So these are, I would maybe focus here, here, and absolutely here. All right, we talked about overfitting. There's a few, they're less prone, random forests are less prone to overfitting than individual decision trees, but overfitting can still occur if your trees are grown too deep. I think you can either reduce the number of features because we're splitting too much, or you can reduce the max depth. I'd recommend to try this one first, reduce max depth. And then to prevent small irrelevant splits, this is the same information from the last slide, you can try min samples at leaf and min samples split. Okay, this is what I wanted to get to. Feature importance. I think we have, let me see how many slides we have after this. 2 slides after this. Time check. Okay, we're doing it. So feature importance here, random forest can provide you feature importance. This is what this actually looks like. What does feature importance look like when we output it? Here are our features that we fed into our random forest. Remember, each tree gets a subset of these features, but this is the entire set of features that we fed to our random forest. This one had the highest importance, meaning it was used the most frequently and at the highest node across the trees, generally speaking, in the random forest. So this is a very predictive, powerfully predictive feature. Fair is also powerfully predictive, age, the gender, and then these are maybe less informative to the model, less informative features to the model's decisions. So feature importance can help us understand how a feature is used within our model, and it can help us explain why the model is making these decisions. We can say, look, these are very informative to the model's decisions. The model considers this information very important in the output that it's generating. So if we're at a different example here, if you have a medical data set and we're trying to predict heart disease, maybe we have a bunch of features going into the model, like cholesterol level, age, blood pressure. We can rank those and we can say, look, the blood pressure is the most important prediction for heart disease. So most important prediction to predict the outcome for heart disease. That's how we can use that to interpret our model results. We have 2 slides here, advantages and disadvantages. Random forest advantage, it can handle missing data a little better. It's great for large data sets. Mostly it's non-parametric. I think that's the advantage compared to linear regression and logistic regression, non-parametric model. Compared to a decision tree, it prevents overfitting, and it's fairly robust to imbalanced data sets. The random forest disadvantages is it's a little more complex. I'm missing a word here. Oh, lack of is supposed to be on this other line. Lack of interpretability. So it's a little more complex. It's not quite as simple as linear regression and logistic regression. There's some more complexity to a random forest. you can no longer say, oh, it's 10 times the number of bedrooms or 10,000 times the number of bedrooms. We have to use feature importance, something that's a little more fuzzy, to explain why the model is making its decisions. Which complexity and interpretability are kind of two sides of the same coin. Because it's more complex, it makes it less interpretable. There can be bias for categorical variables. There is bias towards features with more categories. So there's a little bias in random forest in terms of having higher variability categories. All right, I'm going to keep these annotations, but I want to pop into the code so we can actually start to play around with this. Any questions so far, just conceptually on random forest before we look at the code? I know I kind of flew through that. I told you guys this class is really broad, and then in the next class we get deep into metrics. But you've now learned 4 machine learning algorithms, 4 classes in, and you guys now know linear regression, logistic regression, decision trees, and random forests. Pretty impressive. All right, let's build one, because that's what we're here for. From sklearn.ensemble, we're going to import the random forest classifier. And I think this is, let me check something real quick. Oh, no. I do not have you do a random forest for assignment 3 is on logistic regression. Okay, so you will not have an assignment on random forest. That's what I was looking for. But if you wanted to build one, if you wanted to have a comparison, from sklearn.ensemble, we're going to import random forest classifier. And the great thing about sklearn is the syntax is exactly the same. So if you guys remember the way that we imported linear regression model is equal to linear regression. Probably gonna have to do an import here. I'm seeing if it can. From I'm gonna have to go look this up. There we are. Okay. So if you guys remember from linear regression, it was a linear regression model equals linear regression. We're going to do the same thing for logistic regression. Logistic regression model equals logistic regression, and it's the same thing for a random classifier model. Let's say random forest classifier. So this syntax is exactly the same. It's very, very easy to just switch to a different model. That's the great thing about sklearn is they present a user interface for you guys to interact with that is consistent across models. We can even do a decision tree one. Let's do that. Decision.
So sklearn linear models are already embedded in Colab, or do we have to upload anything?
When you install the sklearn package, it should come with all of these things. The great thing about working with Colab is that you don't have to install that. So for assignment 0, when I had you guys submit that, it verified that you had all the right packages and versions. And one of those packages I verified was sklearn. So as long as you guys ran assignment 0, didn't have any issues, you should be able to run this. And you could even run it locally on your own computer if you wanted, if you just did pip install sklearn. But we won't worry about that. I'm abstracting that from this class. So all these are the same. Here's the 4 models you guys have learned: linear regression, logistic regression, decision tree, random forest. And if we had a data set, the way that you would apply each of these models is, sorry, I keep accidentally doing that, is actually the same as well. But instead of model.fit, we would do, let me put this. What's great is you could make these the same here. The way that you fit all of these models is exactly the same too. So we would call linear regression equals linear regression, and then linear regression dot fit, and you would pass your X train, Y train. Remember, linear regression has to be a regression problem though, so your Y train has to be scalar. Logistic regression has to be classification, so your Y train has to be a category. These are not necessarily the same pieces of data, but it's the same syntax. You would still call .fit on this logistic regression object. And furthermore, you could call .predict, and then you would pass it, X test. This is the same across all of these. So no matter which, I'm just trying to emphasize that no matter which model you are using, it's the same interface, the same pattern. We are instantiating our model by creating a variable name and assigning that model to it after we import it from sklearn. And then we're calling that model .fit, passing our X train, Y train, and then we're calling that model .predict to get our predictions out of the model. That's the same pattern across each of these. This one's just a logistic regression, this one's a decision tree, and this one's a random forest. Does that resonate with you guys? Same interface. That's the power of sklearn. Okay. I am actually going to move this down. There we are. And add a text block here. One interface and working pattern. Okay. So let's import our random forest classifier and let's change some parameters. So what if we talked about all these parameters in that PowerPoint and we said, oh, n estimators, we could try 100, 150, 120. You can change max depth if you don't want to have a deep tree. But how do we do that? It's right here. It's when you create your model. So it's at the instantiation of your model. So up here in all of these, notice these were empty. I wasn't passing any parameters. I was just using the defaults. We're going to change that now. We're going to tell it, look, we want to use 150 and we want a max depth of 7. So we're changing these parameters to our random forest classifier. And we're still going to call model.fit. And we're going to fit to our X train and Y train. I don't think we actually have some, let's create some data. Okay, but we actually have to create that data. There we go. X, Y. There we are. Okay. Now we have X train, Y train data. Here we are. And now we want to make predictions. We can just call model because we called this model up here. So we call model.predict and we pass it in our X test and that will give us YPred. Remember, YPred is what we predicted. So we can see YPred. Here are our predictions. Now we want to see how well we did. We want to compare YPred, score our random forest model using YPred. Here we are. We compare, Y-pred to Y-test is actually what we should be doing. Y-pred. There, accuracy score. Okay, here is our accuracy score. We are comparing Y-test to Y-pred here to generate our accuracy score. So we're saying, what is the accuracy? Here's what our model said the answer was, and here's what the answer was in reality, Y-test, and here's what our model said the answer was, Y-pred. And it was correct 94% of the time. So to this, I've got 94% performance on this fake data that we created. We just generated some like random data here. If we want to get the feature importance out of that model, we can print these feature importances. And this is what it looks like here. So we have 0.07, 0.86, 0.2, and 0.03. Oh, wow. Our most informative feature here is this 0.86. Let's visualize this. I think that'll put a bar chart. Okay, that's fine. It's good enough for now. So there's no labels or anything on here, but this is that feature, and you can see that visually it's predominantly more important. So primarily the random forest is using this one feature, this second feature here, which if we look at our features here, is the most important feature. Let's look at, it's in NumPy array. This is also a NumPy array. Yeah. Which if we look at X, we have 4 columns here. We don't have any column names because they're just generated random numbers, but it's this second column here that is generating, that it's using to make those predictions. We can apply this to your data set that you just worked with. So you guys just worked with the IRIS data set. Let's look at the IRIS data set. Let's train test split the IRIS data set. Let's import our random forest classifier, set our max depth equal to 2 here. And one second. Oh, we're gonna apply cross-validation, which we haven't talked about yet. But we're going to train a bunch of different models and see what we can get the F1 score to be. So in this case, we scored on our test set. We averaged maybe about like 0.96, so about 96% performance on being able to predict the flower type on your IRIS data set. And you guys can even swap out random forest classifier in that existing notebook that you have on your IRIS data set where you're using your logistic regression to predict the class. Okay, let me pause here. Any questions on random forest? All right. If not, I'm going to end the stream and we'll have discussion time. I'm going to end this here.